All right, welcome. These are the solutions for practice quiz C. First question asks, if you have a system of linear equations with 5 equations and 9 unknowns, and that system of linear equations has rank 5, then which of the following statements must be true? So let's disentangle what this means. So first part, 9 unknowns, means there's 9 variables. x1, x2, x3, all the way to x9. And for a system to have a unique solution, each of those variables in the row-reduced matrix would have a corresponding leading 1. The statement that the matrix has rank 5 means that there are 5 leading 1s. So right away we can tell there's no way that this system of linear equations has a unique solution. We only have 5 leading 1s, 9 variables. Up to what I've highlighted so far, we can exclude the unique solution, but can we exclude no solution? Because one of the problems is that we could have a row that reads 0, 0, 0, 0, not 0. Having 9 variables in a matrix with rank 5 doesn't exclude that possibility. However, what does exclude that possibility is that the system of linear equations only has 5 equations. We only have 5 rows. So we look up and say, wait, we got 5 leading 1s, we have 5 rows. There cannot be a 0, 0, 0, 0, not 0 row. So we can eliminate no solution, which means it must have a family of solutions. Now, 9 minus 5 is equal to 4 columns are missing a leading 1. That means we have a system of linear equations with a family of solutions with 4 parameters. So option D. So again, the part of the problem-solving process was comparing the rank of the matrix to the number of unknowns, but we also have to make sure that we exclude the possibility that there's no solution condition, and we can exclude that because the rank is equal to the number of equations. And that just means each row in the matrix has a leading 1. It's not possible to introduce a row that reads 0, 0, 0, 0, not 0. If the question said that the SLE has 6 equations and 9 unknowns, then we couldn't exclude B. We couldn't exclude the possibility that the answer is no solution, unless it said that the matrix is homogeneous. And we can always exclude no solution when it's a homogeneous system of equations. Okay, 2. Which of the following matrices have a rank of 3? Rank means count leading 1s in a row-reduced matrix. Count leading 1s and the RREF. And we want that to be 3. So let's look at the first matrix here. Change my pen color. Blue. Okay, and this matrix clearly has 2 leading 1s. This matrix has rank 2, so it can't be A. We need something to have rank 3. And then the next matrix B, we have a leading 1, we have another leading 1, and we cannot possibly have any additional leading 1s. The leading 1 has to be the first non-zero number in its row, and you cannot have a leading 1 in the same column position as another leading 1. So it has rank 2. It's also not an REF. But if we were to row reduce it, you'd get a row of zeros in the bottom. Okay, second, or third matrix that's here, it's hard to tell because you have 3 rows. The possibility of 3 leading ones is there. We're going to have to do row reduction. I'm going to replace row 1, or row 2 rather, row 2 with row 2 minus row 1. And at the same time, I'm going to replace row 3 with row 3 minus row 1 and make that first leading one happy. And again, the rank calculation strictly does require matrix to be row reduced, but you don't have to row reduce it all the way. You can row reduce it to the point where you're confident you know how many leading ones there will be. Okay, the first subtraction, 1 minus 1, 0, 1 minus 0, 1, 1 minus 1, 0. That's row 2 done. Row 3, 1 minus 1, 0 minus 0, and 1 minus 1. Look at that, row of zeros. Now, this is actually row reduced. You can tell that the rank is 2, not 3. All right, let's keep going. Now this matrix in D is not close to row reduced. I'm going to take row 4. I'm going to divide by 3. I'm going to get 1, 2, 3, 4, 0, 1, 5, 6, 0, 0, 1, 7, 0, 0, 0, 1. So it's not row reduced yet, but we can tell that the rank is 4. There's 4 leading ones inside this matrix. You could take the one on the bottom right and zero out all the numbers above it, and then proceed from there. Proceed zeroing out the numbers to fully row reduce the matrix. And 4 leading ones means rank is 4, which means not 3. Okay, and then the last one must be the answer. You can circle it by elimination, but let's check anyway. So my first step is I'm going to replace row 3 by row 3 minus row 1. And we get 1, 1, 0, 0, 0, 0, 1, 1, 0. So 1 minus 1, 1 minus 1, 1 minus 0, 2 minus 0. Okay, next step. I'm going to take row 3 and replace it by row 3 minus row 2. Okay. So row 1 stays the same. Row 2, 0, 0, 1, 1 stays the same. Row 3 becomes 0 minus 0, 0 minus 0, 1 minus 1, and 2 minus 1. Okay, and then it's not fully row reduced, but it's far enough to tell that there's a leading one, another leading one. There are 3 leading ones. Thus, rank equals 3, as required. Asking us which matrix has a rank of 3, and it was that one has a rank of 3. All right, question 3 asks to find the value of k that causes the determinant to equal 11. You can use your favorite method to calculate the determinant. You can even use a cofactor expansion along pick a row or column, maybe row 1, maybe column 1, maybe row 2. You can do a cofactor expansion. You pick your favorite row, your favorite column. You can row reduce if you want, row reduce it to triangular form. Like take row 3 and subtract row 2. Replace row 3 with row 3 minus row 2. Right? Like there's all types of ways you can solve this. I'm going to use basket weaving, or the so-called secret method. Or I think the fastest way, faster than the secret method, is to replace row 3. Oh no, never mind. I'm a liar. You got to do more work missed the 1 there. It's not really that close to triangular, so I'm not going to do that. Secret method, I'll do that. Super lazy method. But again, it's not necessarily the fastest. Someone could probably finish this 3 times using a faster method in the time it takes me to do this. Okay, so there you go. Make 2 copies of the matrix side by side. And then your determinant is going to be 3 down products minus 3 up products. The first down product, 2 times k times 2, so that's a 4k. Second down product, 1 times 1 times 1, that's 1. And third down product, 0 times 0 times k, so that's 0. Minus the up products, 1 times k times 0, k times 1 times 2, so 2k. And then 2 times 0 times 1, 0. And we don't want that to be equal to 0. We want that to equal 11. Because the question says find the value of k that causes the determinant to be 11. So 11 is equal to 4k plus 1 minus 2k. We don't need all those brackets. 11 is equal to 4k minus 2k is 2k plus 1. We can subtract 1 from both sides. So 10 is equal to 2k, and that means k is equal to 10 over 2, which is 5. Option B. All right. Go on the next page. All right, question 4 asks to calculate the determinant of a string of matrix multiplications. So I'm going to write this out. This is equal to the determinant of A transpose times the determinant of B squared times the determinant of C to the power of negative 1. I'm going to use some shortcuts. Rather than transpose A and take the determinant, we use a property that the determinant, so these are the properties used. First property is that the determinant of A transpose is the determinant of A. The transpose does not change the determinant. So that first property allows us to do this. Second property, not really a property, determinant of B squared is the same thing as the determinant of B times B. And we can use this property again, determinant of B times determinant of B. So I'm going to do that. That's the determinant of B times the determinant of B. And then the last property I'm going to use is the determinant of an inverse of the matrix is 1 over the determinant of the matrix not inversed. So 1 over the determinant of C. We can plug all the data in. Oh, we have to calculate the data. So I have to calculate each of these determinants. A is triangular, or no, it's diagonal actually, even better. What's diagonal? So A is a diagonal matrix. The determinant of A is thus the product of the terms along the diagonal, 2 times a half times negative 2. So 2 times a half is 1, 1 times negative 2 is negative 2. So we get a negative 2 there. The next determinant of B, B is triangular. And the determinant of a triangular matrix is also the product of the terms along the diagonal. So negative 1 times 3, which is negative 3. It's going to get thrown down twice. Once for each determinant of B. And then C is also a triangular matrix. And the determinant of C is 1 times 2 times 3, which is 6. So we'll have a 1 over 6 here. And then we multiply everything together. 3 negatives gives us a negative. We get -3 as the answer. So option A. Question 5 tells us the determinant of a matrix filled with letters is equal to 10. So A, B, C, D, E, F, G, H, I. Okay, so we have the matrix filled with letters, and we're asked for the determinant of a combination of similar letters. So the way this works is we have to manipulate the matrix. It's been kind of like, it's a messed up version of what we're given. We have to unmess it up. We have to disentangle what's been done to it. First step I'm going to do is I'm going to common factor two from row 2 inside that first matrix. Now in the second matrix, notice we have duplicate rows. Row 2 and row 3 are the same. So that's easy. That determinant's just 0. We don't have to bother doing anything else. Okay, so anyways, when we common factor a 2 from row 2, so I'm going to put that 2 out front, and I'm going to write the determinant of the resulting matrix after we do the common factoring, A, D, G, B, E, H, and then C minus 3A, F minus 3D, I minus 3G. Okay, the next step is I'm going to add 3 row 1 to row 3. So I'm going to take row 3 and replace it by row 3 plus 3 row 1. And this is a free move. There's no cost to the determinant. So we get 2 times the determinant of A, D, G, B, E, H, C, F, I. Isn't quite what we have, right? But ABC in the first column looks like ABC in the first row. So the next move I'm going to do is I'm going to transpose, which is also a free move. So we get 2 times the determinant of the first column, ABC, becomes the first row. The second column, DEF, becomes the second row, DEF. And the third column, GHI, becomes the third row, GHI. And that is our original matrix, ABC, DEF, GHI. So we get 2 times 10, which is 20. So option C. All right. And question 6. If the n by n matrix A has a determinant of 10, which of the following statements must be true? Okay, I'm going to go through each one to determine if it's true or not. So for the first statement, statement A, it says for any n, we can say that the determinant of 10A is equal to 100. The property I'm going to use is this one. The determinant of 10, or not 10, but C times A is C to the n times the determinant of A. Because when you multiply a matrix by a scalar, every row gets multiplied by that scalar. And we can use a factoring property to common factor that scalar out of each row. Each time we do that, the determinant picks up one multiple of that scalar. If the matrix has n rows, then it's going to pick up that scalar each time. So each of those n times, if n is equal to 3, it'll be C times C times C. If n is equal to 2, it'll be C times C, and so on. So if we use that property here, the determinant of 10a is going to equal 10 to the n times the determinant of a. So 10 to the power of n times 10, which is not equal to 100 unless n is equal to 1. And the question says for any n, not n is equal to 1. So no, can't be a. Okay, b. If the matrix B is equal to a cubed, then the determinant of B inverse must be negative 1,000. Okay, determinant of B inverse, by definition, is 1 over the determinant of B. And then the question says that B is equal to a to the power of 3, so that's determinant 1 over determinant of a power 3. And then that is 1 over determinant of a times determinant of a times determinant of a. So that's 1 over 10 times 10 times 10, which is 1 over 1,000, which is not negative 1,000. So it can't be B. Okay, C. If n is equal to 6, so this is a 6 by 6 matrix, then the determinant of negative a is equal to negative 10. Let's see what we can say about that. Determinant of negative 1 times a, which is the same thing as negative a, is negative 1 to the n times the determinant of a. And if n is equal to 6, that's going to be negative 1 to the 6 times the determinant of a. And negative 1 to an even power is positive 1. Determinant of a is 10. So we get 10. And the option says negative 10. 10 is not the same thing as negative 10, so it can't be C. Okay. Part D, for any n, it is guaranteed that determinant of a plus a is equal to 20. So that's implying that the determinant of a plus a is equal to determinant of a plus determinant of a. So it'll comment is that the determinant of a plus b is not equal to determinant of a plus determinant of b for general a and b. If either of those or both of them are the zero matrix, then yes, and this is in other situations too, but this is not a property that we could use. Now, that alone does not mean that we can say this is definitely wrong. We can say it's not guaranteed, so I'm going to cross that out. You can make up a matrix that doesn't, two matrices in any particular size that you want, and say, here's an example. Here I did it, and nope, doesn't work. But even better than that is we can simplify this. The determinant of a plus a, so something plus itself is 2 times that thing. Determinant of 2a is 2 to the n times the determinant of a. So 2 to the n times 10 does not equal 20, except if n equals 1. This is a 1 by 1 matrix, then yeah, that's fine. Determinant of 2a is going to be 2 times the determinant of a. Otherwise, it's not true. So since it says for any n, right? So we can circle E by elimination. But let's make sure that it's actually correct. If the determinant of 2a is equal to 80, then n must be 3. Let's check what happens if n is equal to 3. If n is equal to 3, then, well, let's not do the if thing. Let's do it the other way around. Determinant of 2 times a. Hey, erase that. Okay, determinant of 2 times a is 2 to the n times the determinant of a. And it says the determinant of 2 times a is 80. So 80 is equal to 2 to the n times 10. Let's divide both sides by 10. So 80 over 10 is equal to 2 to the n. So 8 is equal to 2 to the n. So this is asking 2 raised to what power gives you 8. Thus, n is equal to 3. There's only one way this can happen. N must be 3. Okay, so that is definitely true. All right, on to the second part. Checking the time on this. Well, it doesn't tell me. Oh well. All right. Part B, long answer question. Show your work for full marks. The question is worth a total of 4 marks. Here's a matrix filled with letters. Yucky, 4 by 4. Don't see any zeros, don't see any duplicates. And we're asked to calculate its determinant, but we also have a bunch of determinants of small matrices. We have the determinant of BCD, FGH, 5 minus 1p. If you look carefully where that's from, that's the matrix you get if you eliminate this and this. BCD, FGH, 5 minus 1p. Now that's a submatrix. It's a submatrix you get when you eliminate row 1, column 1. What this is telling us to do is, not row 1, column 1, row 3, column 1, row 3, column 1. Eliminate this and this, like that. Row 3, column 1. Sorry about that. So this question is basically asking us to calculate the determinant using a cofactor expansion. Must use cofactor expansion. We can't use like row reduction or secret method or anything like that. So I'm going to choose row 3. And we can confirm that when we do the next submatrix, when we do this one, we better get one of the 4 matrices that are down below, A, C, D, E, G, H, M minus 1p, and we do. That's the second one. So we've probably made the right choice. We'll be able to tell if we made a mistake as we go. Okay, so then the determinant of A is equal to A31, C31. So the coefficient in row 3, column 1 of the matrix times the cofactor C31 plus A32, C32 plus A33, C33 plus A34, C34. Okay, next step, I'm going to replace each of these quantities with what they're equal to. C31 is 2, or A31 is 2 rather, so the entry in row 3, column 1. And then C31 is negative 1 to the 3 plus 1 times the determinant of the submatrix A31. And the next entry, A32, is 3 times negative 1 to the 3 plus 2 times the determinant of the submatrix A32. Plus, next entries, we have a k there. Well, that's bad. Let's see what happens. Negative 1 to the 3 plus 3 times the determinant of A33. And the last one is plus 4. So now we're on this number here times negative 1 to the 3 plus 4 times the determinant of the submatrix A34. So let's check what's A33. Cross out row 3, column 3, ABD, EFH. So this matrix here, that's A33. We already determined that we have A32 and A31. Now let's make sure that the last one there really is what we need it to be. If we cross out row 3, cross out column 4, A, B, C, E, F, G, M, 5, minus 1. So that is what it's supposed to be, a 3, 4, that submatrix. Okay, and that's good news because when we calculate those determinants, down below, we can just quote the numbers that are given up above. Okay, so we have 2 times negative 1 to the power 4 times the determinant of A31, which was minus 1 from up above, plus 3 times negative 1 to the power 5 times the determinant of A32, which up above says it's 2, plus k times negative 1 to the power 6 times the determinant of A33, which is 0. Haha, the k disappears, doesn't matter. And then plus 4 times negative 1 to the 7 times the determinant of A34, which is 5. There you go. Okay, I'm going to use a fact here that note negative 1 to the n is equal to 1 if n is even, and equals negative 1 if n is odd. So using that fact, we get 2 times 1 times negative 1 plus 3 times negative 1 times 2 plus big 0 plus 4 times negative 1 times 5. Okay, so negative 2 minus 6 minus 20. So we get negative 28 as the answer. All right. Okay, part B. If the matrix C is equal to A, C, D, E, G, H, M minus 1P, what is the determinant of negative 2C? So which one is this? This is, let's see, A, C, D. Do we have one of those up there? A, C, D. This looks like A32. E, G, H, M minus 1P. So that's A32. Well, okay, so we have the determinant of negative 2 times C is negative 2 to the n times the determinant of C, and n is equal to 3, since 3 by 3 matrix. So we're going to have negative 2 to the power of 3 times the determinant of that matrix. And from up above, the determinant of A32 is 2. So negative 2 to the 3 times 2. Negative 2 to the 3 means negative 2 multiplied by itself 3 times, which is negative 8. Times another 2, we get negative 16 as the answer. That one was quick. Right, and then part C, calculate the determinant of a matrix that looks really bad. EF, 2G, AB, oh my god, what is this? We're going to compare, we're going to look up which matrix has the E, the F, the G, the A, the B, the C, the M, the 15, and the negative 6. Maybe it may not be, I mean, there's a 3M there, so let's just look for the M. So we want E, F, G, A, B, C, and then an M. So let's see. E, F, G, A, B, C, and M. So it has to be A34. This is some like manipulation. Some manipulation of A34. So we're going to have to undo the manipulation. I'm going to take a 3. So I'm going to common factor a 3. From row 3. So take that 3 out. We get 3 times the determinant of E, F, 2G, A, B, 2C, and then 3M divided by 3 is M, 15 divided by 3 is 5, negative 6 divided by 3 is negative 2. Okay, next step is I'm going to common factor a 2 from column 3. So we'll have 3 times 2 times the determinant of E, F, G, A, B, C, M, 5 minus 1. Now let's check E, F, G, A, B, C. E, F, G, A, B, C. Oh, those rows are swapped. We have to swap the rows now. So we're going to do a swap row 2, or not row, yeah, row 2 and row 1. Swap those two rows. And it costs -1 factor. So swapping two rows has an expense for determinants. It picks up a minus sign. So I'll have a -1 times the 3 times the 2 times the swapped rows A, B, C, E, F, G, M, 5 minus 1. And now that's A34. And the determinant of A34, can't remember, is 5. All right. So we're going to have -6 times 5. So the answer is -30. All right, that's the last question.